Okay, now that we have listed and discussed a bit all 6 of the processes that can give rise to either ionizations or recombinations, the nice thing is that we can often simplify the situation. We don't usually need to take into account all 6 of them all the time. As I say here, in many places in astronomy, there's only a subset of the terms that dominate the balance. In other words, if that total right-hand side had a bunch of terms in it, some of them are, of order 1,000, some of them are of order 0.001. So you could ignore the 0.001s. The different regimes where different terms are dominant usually depends on the density of the gas or the plasma, right? High density, medium density, low density. What that means exactly, we won't delve into, but generally the high density, we're talking about regions that are close to thermodynamic equilibrium, right? We used this term LTE before, and well, yeah, one of the aspects of LTE was the idea of detailed balance. Remember, all of the upward photon transitions were balanced by downward photon transitions. All of the upward collisional transitions were balanced by downward collisional transitions. And here that is similar. So we can actually derive the ionization balance when everything is in LTE in one of 2 ways, and you'll get the same answer. This is called Saha's ionization balance equilibrium. We'll talk about that in a second. And it's very convenient, again, that you can do it by either the photons or the particles, because everything is in good communication with each other. There's a single temperature, there's a single thermodynamic equilibrium for all those different particles. But as we go to lower density environments in astronomy, for example, the corona of the sun, or other very hot plasmas, say in the vicinity of stars, or say galactic central regions, AGN regions, often obey this sort of intermediate type of ionization balance called coronal equilibrium. We'll talk about that, where there's essentially no more photoionization and there's no more 3-body recombination. The 3-body recombination only works when the density is high. The photoionization only happens when you're when you're in close proximity to a source of very high energy photons that can ionize atoms. Neither of those seems to be the case in coronas a lot, so it's the other 4. At the lowest density regions, say in the interstellar medium, in nebulae in the interstellar medium, planetary nebula, all sorts of gaseous clouds out there, like Hubble's pillars of creation, things like that. It's the lowest density region. Most of the collisional processes go away, and if you're in the vicinity of a bright photoionizing source, like a hot blue-white star, then that source of ionizations can be balanced by other radiative processes, and we'll talk about that too. So yeah, the first idea is this high-density detailed balance that's called Saha's ionization balance equation. And as I said, you can do the bookkeeping with either just the photons or just the collisional excitations and de-excitations. And the answer you get, well, it's a kind of a complicated equation. You have to write up a whole sum of different ratios. As we said before, you can write those out in equilibrium by just the ionizations and recombinations between those 2 levels. This right-hand side has a lot of different terms in it, and unfortunately, it's kind of complicated. It's got the number density of free electrons, and you need some free electrons around for things to be colliding, for example. It's got the de Broglie wavelength of a free electron, and in a way, the product, I should clear that up, the product of the cube of the de Broglie wavelength is kind of a volume. The number density of free electrons is kind of a 1 over number per volume. So this is sort of telling you about the total number of free electrons within a de Broglie sphere, almost. These other things tend to depend very much on temperature. Oh, and so does the de Broglie wavelength. But everything else over here is kind of an increasing function of temperature that depends on the ionization potential, essentially the energy difference between the two ground states of the two adjacent ionization stages. But yeah, it's very much an increasing function of temperature. So on the right is an example for hydrogen. As the temperature goes up, the amount of hydrogen that's ionized, right? So for hydrogen, there's only two stages. Now this is just an N1 for the ionized state over N0, the neutral state. And at low temperatures, this is going to be a low number because it's all going to be in the denominator. And then at high temperatures, it'll be a big number because it's all in the numerator. And where the transition happens, where's the halfway point where hydrogen is half ionized and half neutral? Well, that depends on the number density that comes into play in Saha's equation there. Yeah, I'm not sure how much else to say about that. This is something that's very important, for example, in the interiors of stars. If you want to figure out what is the ionization stage at different layers in the interiors of stars, this is the go-to equation. Okay, well, let's go on to the next lower density regime, the so-called coronal regime. This is generally the regime of hot plasmas. Density is too low for LTE, for the thermodynamic equilibrium approximation. And again, usually there's not a source of ionizing photons around. It might seem a little strange to talk about a lack of photons when we're talking about the solar corona, right in the vicinity of the solar atmosphere, where there are a lot of photons. Unfortunately, the solar spectrum, peaks right in the visible wavelengths. Most of these ionizing photons are much higher energy, up in the ultraviolet and X-ray. So we still can ignore photoionizations here. That means there's the other four: collisional, autoionization, radiative recombination, and dielectronic recombination. And the convenient thing here is, if you remember, these four processes were the ones that we noticed in the previous video had a rate. Each one of those rates was linearly proportional to the number density of free electrons. So guess what? If there's a factor of any in every term in the numerator, and there's a factor of any in every term in the denominator, they just cancel out. So what's left is just a function of temperature only, which actually makes this coronal ionization balance the easiest one to compute, because it's just a function of temperature, doesn't depend on anything else. So for example, in the picture here is an example for oxygen, right? As the temperature goes up, and this x-axis is in the log. So yeah, 4 means a temperature of 10 to the 4th Kelvin, 10 to the 5, 10 to the 6. So very, very high temperatures. The relative fraction, again, it's a log, so 1 would be 0 here. So when something is hovering up here at 1, it's the dominant stage, and everything else is much lower. So it's neutral, then singly, doubly, triply, all the way up to 8 times ionized oxygen when we're at temperatures of 10 to 100 million kelvins. Oxygen is fully stripped. There are no electrons left. It's only just bare nuclei and free electrons. That's what we mean by O8+. So yeah, that's the coronal the coronal ionization recombination balance. And I did want to just do one sort of mini derivation, because all of these equations are just giving us these pairwise ratios, and it would be nice just to see, how do we get these absolute fractions, right? These fractions are essentially Ni over the total over all of the different ionization stages. How do we actually get these absolute fractions out of these pairwise fractions? And we'll look at that in a second.
Well, how do we get the absolute fractions of a given ionization state if all we know from the equations are these relative rates? So let's look at an example here of a 5-stage atom, right? So all we know is N1 over N0, N2 over N1, N3 over N2, and N4 over N3, just the adjacent ratios. The other thing we know is that the total number density over everything is just a sum over all those. Right, 5 terms there. Well, here's the trick. It's a mathematical trick, sort of. we divide everything here by this n total. So the left-hand side is 1, and each term. Now, these are the fractional things that we want. Whoops. I hope you don't mind if I'll just do ... to do all the rest. It's just the sum of these fractions that all have to equal 1. Well, let's rewrite this right-hand side a little bit. Let's take out a factor of n0 over n total. That means that the first term is 1. The second term, well, what if we just wrote n1 over n0? That n1 over n0 multiplied by the thing outside, right, this times this is just n1 over n total, which is what we wanted to begin with. The second term, the third term, we can write as n2 over n1 times n1 over n0. And then all the other terms are ... like that. Right, so let's say, this third term is supposed to be n2 over n total. Well, is it? There's an n2, the n1s cancel, the n0s cancel, and whoops, n total is that denominator there. So that is what we have broken it down to. Let me just remind us that that's a 1, and let me erase these terms up here. And what do we get? Well, let's call this thing in square brackets. Let's just call that sigma for sum, and it's basically made up only of these pairwise ratios that we already know. So we know sigma. That means that we can write n0 over n total as just sigma. Multiply both sides. Oh, I'm sorry. No. It is, in fact, 1 over sigma, because the sigma is in the numerator on the right, so it'll be in the denominator on the left. And then we can just use all the ratios again, right? If we want n1 over n total, it'll just be n1 over n0 times n0 over n total, which is 1 over sigma. So we've built it up from these pairwise ratios. And 2 over n total is just going to be n2 over n1 times n1 over n0 times n0 over n total, which is just 1 over sigma again. So it is possible to use these pairwise ratios to build up the absolute fractions.
Okay, well, that's it essentially for the coronal plasma ionization balance. The final one that I wanted to talk about is the so-called nebular ionization balance. This happens, as I say here, in very low density regions where collisions are very infrequent because the density is so low. And it's also far from LTE, so there's really no detailed balance. There are sources of ionizing photons if you're nearby something like a very hot star with a lot of UV photons coming from it. And then the recombinations that balance it out are all radiative recombinations. So they're limited by how many electrons are around, but they're really all that's left since there are no collisions. The photoionization rate can be sort of built up from various pieces. I think we've seen before what this thing here is. This is the mean intensity, right? It's the intensity of radiation integrated over all solid angles and then divided by 4 pi solid angles. So it's like taking the average intensity. Remember, these atomic processes don't care that much about whether where the radiation is coming from or where it's going. It's just, is there a big source of photons around? Are we sitting in a bath of photons? And that's the average mean intensity that we're talking about. These other quantities, basically you have to integrate over the entire spectrum. The energy units in the intensity are divided by another unit of energy, h nu, to get a rate. This is, remember, just how many events are happening per second. So many of the units have to cancel out. What's left is this sigma that we call the cross section. Essentially, how big does the atom look to an incoming photon? How big is the target? So it's very much like the area of a target. Also, it's similar to the photoelectric effect, right? You're shining ionizing photons on something, and it's going to eject electrons because the atoms are being ionized. And just like the photoelectric effect, there's this sort of strict on-off threshold. If the energy of the photons are lower than the ionization threshold, right, this difference in energies between the ground states of the two adjacent ionization states of the atom, then nothing's going to happen, right? There's no ionizations that can happen if you can't give a bound electron enough energy to escape. Once you're above that threshold, you can. The cross-section has a finite value. It's got this weird 1 over frequency cubed dependence on it that you can see here in the plot on the left. But the big takeaway is that it's 0 to the left of the threshold and non-zero to the right of the threshold, which is what we suspected for this kind of thing. For stars in the interstellar medium, they're typically surrounded by gas, which might have started off as cool atomic, say, hydrogen in the interstellar medium. But once the star turns on, these ionizing photons go out, and they ionize a certain region around it. This is called an H2 region, right? An ionized hydrogen region, sometimes called a Stromgren sphere, because Bengt Stromgren worked it out in the 1930s, how big it should be for a given source of photons. It can only be a finite size. It can't go on forever, because when each photon that's being emitted by the star gets absorbed and allows a given atom to be ionized, that photon is gone. So the photons eventually get used up close to the star, and then once they're gone, there's sort of a sharp edge to this region. There's ionized gas inside, neutral gas outside. It's never an exact sphere, but it's sort of a 50 parsec diameter region. And I guess one thing I did was I just went into Google Images and looked for Stromgren spheres. And, these are the types of compact emission line nebulae that one finds, right? There's the planetary nebula, other types of relatively compact nebulas that one can see in space. Okay, I think that brings to an end our module on spectroscopy and using spectra for learning about astronomical objects. Final topic of the course will be nuclear physics, and we will get into that in the next video.